So that's what a for loop is. Huh. Interesting. Dog ear that page. For the last couple weeks, we've studied data structures. 2 weeks ago, we learned about lists. Last week, we learned about strings. And this week, we're going to learn about something a little different and a little more orderly, the dictionary. So we have lists and we have strings. Why do we need another data structure? If you've noticed some things about lists or strings, you've noticed that the order in which we add things to them matters. And yes, we can shake them up and we can fish things out of them and we can find items by index or by name. But if we want to represent something with more than just one dimension of information, and we're going to start referring to the ways in which data structures hold information as their dimensionality. If we want to represent something like a table, rather than something that's just like a 1 to n list, we're going to need something a little bit more complex. And dictionaries allow us to do that. They allow us to organize our data according to things called keys, which give us a little bit more control over how we catalog what we find. And organization is key. Lists can store whatever we add to them in the order we add it, but we're really not looking for complex relationships between the data. We're just looking to see if values are there. For example, if I wanted to call up my first cat in my cat names list, I would say cat names 0, cat names 1, Snooze Magoo, Mr. U. Both of those are wonderful names. But if I were to use this in the form of a dictionary, which allows me to give additional dimensionality or additional texture to the data, it might look more like this. And what you notice here is a few things that are key. First, they're set off by curly braces rather than brackets. But second, and most importantly, in terms of our organizational conversation, they don't use indexes. They use keys. And you notice that by looking at the way that the pairs are arranged on a given line. For example, on the first line, I say Snooze Magoo as a string, a number. That allows me to mix data types. When we were talking about lists, we said it's probably not best to mix data types in a list because you lose track of what's in there. With dictionaries, it's almost required. Again, this first thing, the key and the value, this is called a key-value pair. This allows us to simulate a tabular version or something that allows me to keep more detailed or discrete data about the names I call my cat, which is a very, very big benefit for me. And beyond the braces and the key-value pair idea, when we read this, it's not too dissimilar from a list. We still have an identifier, we still have commas separating each key-value pair to let us know where one begins and one ends. And the way that we access them, as we're going to see in this video, is through something called subscript notation, which looks similar to the way that we grabbed indexes from lists. Later on in this video series, we're going to see methods that allow us to work with dictionaries a little bit more directly. But for now, subscript notation is an easy way for us to get into using dictionaries and see how keys work. And here I have my dictionary. You'll see that I have each of my key value pairs separated by a comma, and all my keys on the left side of the colon and all my values are on the right. And if I want to get the first item here, Snooze Magoo, I don't use an index. I don't call it at cat names 0. If I were to do that, print cat names 0, there's an error. There is no such key as 0. So we're not looking at indexes anymore. We are looking specifically at text keys in this dictionary specifically. You're going to follow whatever data type is in the key on the left side of that colon as the way for you to call up the item. So if I wanted to fix this, I could call up Snooze Magoo, print out, and I get my 8. Similar to other entries, if I wanted to print, for example, cat names, and I want to print his proper name, of course, I don't call him it that much, but deserves to be shown, I get my 1. And this starts to look a little bit like lists with the exception that I'm using keys in the spot where the index used to be. And if it's true that I'm considering dictionaries to work like lists, in some respects, I might be able to intuit that I can also iterate or loop through my data structure to get each value and key separately. So I'm going to try that out. I'm going to say for name in cat names, just like we started our list last time. But I'm going to print name. I'd like you to take a second just to intuit what you think we might get when we print name. And what we get is a little informative as to, well, how we're actually going to use our data structure to our advantage. So let's go ahead and print it. and we get Snooze Magoo, Mr. U. We get all of the keys associated with the dictionary here. But what if we want both the keys and the values? Well, using some principles that we already know, we can derive how to do that. And you might already have an idea of how we are going to do that as well. Use an F string just to show it because it demonstrates what I'm talking about a little bit more clearly. I'm going to print the name here. So I'm looking at just the key that I find with a colon. And then across the way, I'm going to put the cat names. And if I want to access the value of a given key, again, I just have to call it up by name. Now, we already have something that stores the key values that we're looking at in this dictionary. It is the variable name for the same reason that it works on lists. For element in data structure, it works here just as well. And if we use name to allow us to call that up dynamically, that is, we don't have to search for it specifically. We just use the for loop to do all the searching for us, and we print it. We should get something a little bit more print-friendly. And we do. So we get our keys and values printed in a little bit more useful of a way, but we also see that we can access our values directly. And we can find that we can use these data structures, these dictionaries, in different ways to help us do cataloging problems. In this case, you're going to help me with the very existential problem of my cat and I watching birds out of our window and counting how many birds we've seen of given types. And no, I have no idea what a grackle is. I just think it's the coolest word ever. So it's there. It's probably like a large hamster, rodent, crow thing. I have no idea. But I've already created a birds dictionary for myself. And you'll notice that just like when we create empty lists, we use the bounding symbols of the data structure to denote an empty dictionary. So it's the empty curly braces. Now I'm going to loop over my list here for bird in birds seen, just to demonstrate that all I'm doing is printing over my list. And we can compare and see that they are in fact the same. But lists are my data source. They're the thing that I've been keeping in order to catalog all of these birds. So I just want to prove to myself that I see what's in my data structure. Now, to add things to a dictionary, we're going to use a conditional, and we're going to use something we've been using recently to ask questions of whether or not values are present in a given dictionary. We're going to use the if, and we're going to ask if the bird is in fact in birds. And this is going to search the keys and say, all right, is there a crow key? Is there a grackle key, a sparrow key? And in the case that it's there, we can assume that we want to add one to it. So we want to increment the amount of birds we've seen of that type. So we could say bird, again, calling by the key that we want to look for or that we want to sum it up, plus equals 1. However, if it's not in the dictionary, so I'm going to run this, and if it's not in the dictionary, we're going to see that, well, nothing really gets added. So if I print birds, nothing's there. Well, because there was nothing in the dictionary to begin with. I need to actually add my keys. Now, if I need to do that, I have a kind of two-state problem here. I have this if bird and birds. I'm asking if it's there, add 1. But I'm not doing anything in the case that it's not there. So else, this is a two-state problem. I want to create a key, and I can assume that this is the first time that I've seen the bird. So then I can even loop through my list after I print it here first time. I'm going to say print birds. And I can see that now I have counted up all the different birds I've seen. It looks like pigeons are winning. That may or may not be factual. I could, of course, for bird in birds, print and use my F string here. Bird, colon. I'll actually use a tab. It's prettier. Birds, bird, just like we were using above with name, cat names. Print a nice little list of all of the birds that the boss and I have seen in a nice little order. And we can again see that pigeons edge crows by 1, sparrows come in a third, and the grackle, which again I have no idea what it is, comes in last. So what did we learn? Well, we learned about dictionaries. We saw dictionaries for the first time. We saw their syntax, but most importantly, we learned that they do not operate on indexes. We do not use numbers to call up things that we want to get out of them. We use keys. Now, in this video, we saw really 2 one-dimensional dictionaries. There's only one level of key-value pairs. In this course, we're really only going to go as deep as about 2, but we'll see that in future videos as we learn more methods of dictionaries and other ways of working with them.